and they are started on page 3 of your packet. Having some colored pencils might be a good idea. We're going to color code some graphs. So this unit is really applications of integration. We've kind of learned the nuts and bolts of integrating in Unit 6. And then in Unit 7, we kind of brought in the idea of a differential equation being nothing more than a derivative, but that led to integration and applied the nuts and bolts in Unit 7. And so Unit 8 is still further applications and contextual applications, things like that. So for today, we're going to talk about something called an average value. And this can be inherently confusing because we've dealt with things like average rate of change. And now we bring in this term average value, and sometimes people get them confused. So we're going to try to adjust that confusion and sort that out. So average value of a function over an interval or on an interval, our central question today is literally, what is the average value of a function? What does that mean? So when we talk about an average value of a function, I'm going to talk about this through the context of this question. We're saying, hey, here I have this function. In this case, it's a parabola, right? Upside down parabola. We can kind of see it extending beneath the axis here. So I have this function, and I want to look at their values in this domain from -1 to 4. That's what that is saying. And so if we look at the function's values over this domain, we can see that they range anywhere from 0 to a little over 6. And so the idea is then if we have all of those function values, then what is the average value? And the idea of the average value is where does that horizontal line sit, so that when we look at the this parabolic function and we look at the area underneath the curve, where do we have to put this horizontal line to achieve a rectangular region across this domain with the same area? So let's kind of look at that graphically. So here is that same function. If we integrate and evaluate the definite integral, we'll see in just a few minutes that this average, or this area, excuse me, is 20.83. And of course, we're in this domain from -1 to 4. If we were in a different domain, we would have a different area, right? If we went just from 2 to 4, we would have a much smaller area. Or if we went out from -2 to 5, we would have to incorporate some negative regions. So, so the domain's important. So this domain is going from -1 to 4. The domain width then basically is 5 units. So what we want to do is we want to replace this function with what we call a constant function. That's what a horizontal line is. It's a constant function. So we want to replace this. In fact, I'm going to take away the parabola for just a minute. I want to replace that blue region with this green region. That's a rectangular shape. And then the top value, or the top of this rectangle, that horizontal line, which we could call a constant function, that is then the top of the rectangle. And the rectangle then will have the same area as that. I'm going to bring the parabola back now, as that parabola, as the area underneath the parabola does. So that is the definition of the average value. Is, hey, I want to take this irregular shape, this blue shape. I want to take this blue shape and replace the blue shape with this green rectangle. And so the idea of having a constant function here basically is saying, I don't want my function values to vary from 0 to a little over 6. I want my function values all to be the single value, which ends up being 4.17. So how does that look algebraically? Well, we're going to have to decide, the ultimate goal is to find the height of that rectangle. So to find the location of that horizontal line. And so the first thing we need to do then is, integrate to find the area underneath this curve. So we're going to integrate that function over the domain from -1 to 4. So going through this integration, then I'm going to go just kind of hit the highlights here, right? Integrating this function is -x cubed over 3. Integrating this is going to be 3x squared over 2. Integrating this is going to be 4x. And we're going to evaluate that from -1 to 4. And so we know that means plugging in, you know, when we have to evaluate this, it means plugging in 4 and then subtracting when we plug in 1. So it kind of looks like this, right? We plug in 4 everywhere. We're going to have to get that answer. And then we subtract, and then we plug in -1. So without getting too much into the computation here, when I evaluate plugging in 4, I get 56 over 3. And when I evaluate plugging in -1, I get a -13 over 6. So subtracting a -13 over 6 is the same as adding. If we put this over 6, it looks like it's 112 over 6. So 112 plus 13 is 125 over 6. Ignore those brackets. I just forgot to take them out. So that's the area underneath the function. If we take 125 divided by 6, you get 2023. So now we want to find that average value. So that average value then is taking that area and converting that area into the shape of a rectangle. And so that rectangle is going to have a width of 5 and a height of whatever we calculate. So we know the area of a rectangle then is base times height. So here's the base, here's the height, or we could call this, you know, the width times the height. And that height is literally the average value. So I'm going to divide out the width here. I'm going to divide by 5. I get 125 over 30. If I take that 125 divided by 30, I end up with 14.17. So the average value is quite literally taking away the blue irregular region and replacing it with the green square region. So why don't you pause the video for just a second here and go ahead and get the annotation to the graph down, because all you have is this parabolic region. Go ahead and annotate the graph to get the rectangular region in your notes, as well as the steps for the integration and then finding the average value. Okay, so then moving on, then let's go ahead and nail down the definition of the average value. So the average value of a function is a constant function. It's a horizontal line, and that horizontal line yields a rectangular region underneath it having the same width and the area equal to the value of the integral of the original function. So what we are looking at mathematically then is we're looking at integrating the function from a to b, so that from that domain, and then dividing out, so we get that area, dividing out then the width of the domain, which is b minus a. And when we divide that out, then we get a single value that's across that entire region, and we call that the average value. And that generates that rectangular region with a constant function on top. So just to kind of go through a quick example here, we've had something similar to this where we've given you a function and we've just told you the values of the regions between the function and the horizontal axis. So let's take this and make it into an average value question. So the question is, what is the average value of g of x on the interval from -7 to 5? So we know we need to integrate g of x from -7 to 5, and then we need to divide by the width of that interval, which is just the final coordinate minus the initial coordinate. Okay, so looking at this then, we're just summing up the regions that we see. So we have -5 plus 3 minus 8 all over 12. That's the width of the region that we're looking at. And so we can have this region crossing the x-axis. It doesn't affect the calculation for the average value. So calculating this out, we get -10 over 12. So we notice that when we have a larger region or regions that are below the axis, we have the potential of having a negative average value. That just means that that rectangle that we draw is underneath the horizontal axis. So this average value would be -5/6. All right, so here's an example. Again, the question is, what is the average value of this function over the interval of 0 to 2? And so we're looking again to take the region underneath this function between 0 and 2 and convert it into a rectangle. So to get that visual, to kind of hold on to that visual of, hey, I want to take this irregular region and then I want to make it into a rectangle, that really helps the kind of form the conception of what it is you're trying to look for. So try to keep that kind of in your mind. Okay, so we know that finding the area underneath this region involves integrating this. And if you notice, it's going to be a U sub. So we're going to use that tip that says when we think we have a U sub, if we have a radical, we make the stuff in the radical the U. So our U is x cubed plus 1. And then we have to differentiate that. So du dx is 3x squared. And then we have to solve for dx to prepare for the substitution. So I'm going to do the old switcheroo here. Dx is du over 3x squared. And now I can start substituting this into the integrand. We know the x squared stays because that will end up canceling out. So I'm going to go ahead and do the substitution. Notice I've taken off the upper and the lower limits because I am going to start to remove the x's and substitute them in with u's, and I'll take care of reestablishing those limits in terms of u later on. Okay, so we have x squared here. Now I'm going to substitute out this, so that's going to become the square root of u, and then I'm going to substitute out this with this, and that's going to become du over 3x squared. And then we notice the x squareds canceled, right? These u subs are very specific. That will always happen. And then we have a 1/3 here, and I'm going to bring the 1/3 out to the outside, and then I have a much simpler integration of the square root of u du. And then I'm going to recognize this is a power, so I'm going to rewrite it as u to the half power so that I can reverse my power rule. So reversing the power rule says bump this up by 1, so it's u to the 3/2, and divide by that new power, 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So that's what I'm going to do here. I'm going to multiply by 2/3 and get 2/9, u to the 3/2. Now that I've done basically the antiderivative, I can start addressing these new limits now. So my upper limit, when x is equal to 2, I put 2 into here and I get a u. So 2 cubed plus 1 is 9. And when x is equal to 0, I put 0 into here and I get a new lower limit. So 0 cubed plus 1 is 1. So my limits in terms of variable u are 9 and 1. So I'm going to add that to the notation. So I have 2/9 u to the 3/2, and I'm going to evaluate that from 1 to 9. And so I'm going to go ahead and plug in the 9 and then subtract and plug in the 1. There we go. I'll keep the 2/9 outside. And now I have to evaluate this, and we should be able to evaluate this without a calculator. Remember, we do the square rooting first. So we look at this notation and we say the square root of 9, that's what the 2 is. The square root of 9 is 3, and 3 cubed is 27. And then we do the same thing here. Square root of 1 is 1, and 1 cubed is still 1. 27 minus 1 is 26. I'm going to take 26 and multiply it by 2 to get 52. So the value of the integration is 52 over 9. So I need a rectangle in order to find the average value. I need a rectangle that has an area of 52 over 9 and has a width of 2. So I'm going to find the height of that rectangle, and that's the average value. So the area is 52 over 9. I'm going to divide it by the width of the interval, which is 2. That's if I divide by 2, I basically can divide the top by 2. So this ends up being 26 over 9, and that's the average value for this function over the interval of 0 to 2. Okay, so here's another example. So again, try to pause the video and try to do this one on your own. Okay, if you're tuning back in, I'm assuming you pause the video and try to do this one on your own. So we know we have to integrate 2 cosine x from negative pi over 2 to pi over 2. Integrating 2 cosine x because it's 2 sine x. We have to evaluate that from negative pi over 2 to pi over 2. So I'm going to substitute those, the upper and the lower bound in. And then we have to think about our unit circle here, because again, we should be able to do this without a calculator. So let's think about the unit circle. Pi over 2 is the top of the unit circle, and sine is the y coordinate. So top of the unit circle has a y coordinate of 1. So this is 2 times 1. Now let's go over here. Negative pi over 2 is the bottom of the unit circle. Sine, again, is the y coordinate. So the y coordinate at the bottom of the unit circle is -1. So this is 2 times -1. So substituting in those values, we get 2 times 1 minus 2 times -1. And then doing this math, we get 4. So we know that the area is 4. So now we can question that average value. We know we want to make a rectangle with area 4, and the width is going to be the width of this domain. And so the width of that domain is going to be pi over 2 minus -pi over 2. So adding these together, because minus and negative is a positive, we get pi. So our average value then is 4 divided by pi. All right, so before we go on to the last example, we're now going to finally address the points of confusion, really. We've been talking about average value. We know it involves integration. We know it involves finding an average function value. It's like, you know, we have this domain. We have a variety of function values across the domain. We want the average of those values. That's what this is about. The problem is that this is confusing because we use the term average rate of change when we do some differentiation. So let's try to address the differences between those and how to identify which one they're asking you to do. So why don't you wait a few minutes to take the notes and just kind of listen, and then you can pause the video to take the notes. Okay, so we've got these two terms, average value and average rate of change, right? Average ROC is what we would call this. And we know from today's discussion that the average value involves taking the integral and finding that area and then dividing it by the domain width, right? So if we look at this geometrically, this integral gives us the area of the rectangle, and this is our base. So this must be our height, right? Because base times height is area. The average rate, though, the average rate of change, we know is the algebra slope. So while average value involves integration, average rate of change involves differentiation. So two very different processes. So let's convert these into mathematical representations, right? This is how we find the area. This is the domain width. Algebra slope is rise over run. Notice that the denominators of each expression are the same. Okay, it's what they're asking you to do in the numerator. That's the big difference. So how do we distinguish what they're asking for? Really, it boils down to looking at what you're given and then looking at what they're asking you to find. Okay, so let's take a look at these two terms, average value and average rate of change. Let's go back to the beginning of the year when we started talking about average rate of change, right? We started saying, oh, it's the algebra slope, right? We got 2 points on f of x. That's what we're given. And we want to find the slope between those 2 points, right? And it's basically used to approximate the derivative. So that's the key, is that the average rate of change gives you information about a function and asks you something about its derivative. So what they're giving you and what they're asking for are two different things. That's the key. Okay, that's when you know you need to use the average rate of change. So when you're given something and then we're asking to find its derivative or information or approximation about its derivative. Okay, how is this different? How is the average value different? Oh yeah, we call that f prime of x. Okay, the average value is different because you're given information about a function and you're asked to find information about that same function. You're saying, hey, here's f of x. What's the average of f of x? Okay, so you're not being asked about something different. You're being asked about something that's the same. That's when you know. So you're being asked about what you were given. Given f of x, you're being asked about f of x. That's when you know you need to use this, and that's the key. Those are the key phrases to look for to figure out which one they're asking for. And so this average value is a f of x value, where this average rate of change is a derivative value or an approximation of the derivative because it is an algebra calculation. Okay, so at this point, you can go ahead and stop the video and take these notes here. You don't have to take down the red stuff, but everything else. And after you get done taking down these notes, we're going to look at an example where this gets confusing, and we're going to try to, find this information here to know that we're supposed to do this. Okay, if you're tuning in, we're going to hit this last example now. So we have a 12,000 liter tank of water, and it's filled to capacity, so it's filled all the way up. At time t equals 0, water begins to drain from the tank at a rate modeled by R of t. R of t is measured in liters per hours, and R is a piecewise function defined as you see here. Okay, so what are we given? We're given R. Okay, and let's not get too into this, but we're going to address why this can be super extra confusing. But you are given R. So what are you being asked? You're being asked to find the average of R. So when I say R is a rate, I'm saying that because this is what they said right here. Okay, we're given water begins to drain from the tank at a rate modeled by R of t. So R of t is a rate. And we're being asked to find the average rate. So this can be super confusing because this looks like average rate of change, and it's not. What we're being asked to, because this is a rate, because we're given a function that's already a derivative, so to speak. Since we're given a rate, all we're really being asked to do is average that function, R of t. Okay, it can get really confusing. So we know that this is an average value question. Okay, so we're given R of t, we're being asked to average R of t. We're being asked about the same thing that we're given. So we know it's an average, value question. So what is the average value? Well, we know we need to integrate from 0 to 8, because if we read on this for the rest of this question, we know that we're looking at the domain from time t equals 0 to t equals 8, and then we have to divide it by the width, which is 8. So this is a calculator question, so I'm going to do this integration on my calculator. It's a piecewise, so we're going to have to put this together in 2 pieces. We're going to have to integrate this from 0 to 5, and that's going to be one region, and then we're going to have to integrate this from 5 to 8, and we're going to have to add those regions together. So that's kind of, that's the nice thing about integration, is you can just keep adding them together. It's like taping shapes together on a graph, right? We can just keep adding them together. So let me get my calculator out here and put this into my calculator. So here it is in my calculator. Maybe that's not the best way of doing that. Let me just clear everything out. Okay, so we're going to do a math 9. And we're going to go from 0 to 5 across that first function. So what was that first function? 600t divided by t plus 3. Okay, so 600, so 600t, but the variable we have in our calculator is x, divided by, now we need brackets here, x plus 3, right? We need to divide by that binomial. Okay, and we're integrating with respect to x. Okay, then to that, we're going to add, we can do this, we can put a bunch of math 9s on the same row. We're going to add from 5 to 8, right? Because that bottom function is only available when we're bigger, or only applicable when we're bigger than t equals 5 hours. And that's 1000 e to the minus 0.2t. 1000 e to the minus 0.2t. And we're integrating that with respect to variable x. So the value of that area is 2064.42196. So I'm going to take all of those decimals, all of these places here, because it's an intermediate calculation, so I don't want to round yet. So I'm going to go ahead and integrate, and that means we have 2 integrations to do on our calculator, and we can do that all in one step. And we get 2064.42196. So now I'm going to divide by 8, and that's when I'm going to finally do my rounding. So I'm going to take that answer and divide it by 8, and I get an average value of 258 point. And now I could take all these decimals and write them down. That will be fine if you want to do that. But we really can stop where we see it 2. So we can either write a 2, that's fine as well, or we can round this appropriately to a 3, which would be fine as well. And I think I did round it. So we have 2.58, or 258.053 as our average value. And we know if this is an average value, it's just asking us to average what we already have, this function we already have, that we know the units are the same as what we have, which is liters per hour. So that's the average value over that 8-hour time period. Okay, so when we get back into the classroom, then we will look at our takeaways. The average value is kind of a unique application because it really allows us to take these irregular shapes and make them into rectangles. It allows us to take several regions, that are just consecutively positioned across a domain and just add them together. So it has some real nice applications. But we'll talk more about those as we work through the topic questions and as we go through the takeaways.